So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's almost certainly a battery within arm's reach. Maybe it's in the phone on your nightstand, or the laptop you just closed, or that little remote control somewhere in the sheets. There might be one in a watch on your wrist, or in a smoke detector on the ceiling above you. Batteries are so ordinary, so completely woven into the fabric of daily life, that we barely notice them anymore. But if you were to peel back the casing of any one of those little power cells and really look at what's happening inside, I mean really understand it, atom by atom, you'd find one of the most elegant and quietly astonishing processes in all of science. A controlled chemical reaction, converting the energy stored in molecular bonds directly into a stream of electrons that can do work. No fire, no spinning turbines, no steam, just chemistry becoming electricity, silently, in the dark, in your pocket. And the story of how we figured that out, how we went from having absolutely no concept of electrical current to carrying around these tiny rectangles of portable power. That story stretches back more than 2 centuries, and it starts in a place you might not expect. It starts with dead frogs. Let me take you to Bologna, Italy, in the late 1780s. There's a man named Luigi Galvani, and he's a physician and anatomist at the University of Bologna. He's well respected, meticulous, the kind of researcher who keeps careful notes. And Galvani is interested in something that a lot of natural philosophers were interested in at the time, which is the relationship between electricity and life. This was an era when people were genuinely unsure whether electricity was some kind of vital fluid, something living things generated on their own, or whether it was a purely physical phenomenon like gravity or magnetism. The boundaries between biology and physics were blurry in a way that's hard for us to imagine now. So Galvani is doing dissections. Specifically, he's working with frog legs, skinned, detached frog legs pinned to a table. And during one of these sessions, something strange happens. One of his assistants touches a scalpel to a nerve in the frog's leg, and at the same moment, a nearby electrostatic machine happens to produce a spark. The leg twitches. It kicks as if the frog were still alive. Now, you have to understand how startling this would have been. The frog is dead. The leg is severed from the body. And yet, it moves. Galvani is fascinated. He starts experimenting deliberately, touching different metals to the nerves and muscles of frog legs, and he keeps getting these twitches. He tries it outdoors, hanging frog legs from iron railings with brass hooks, and the legs twitch again when the wind blows them against the iron. He becomes convinced that he's discovered something profound, what he calls animal electricity. He believes the frogs themselves are generating electrical charge, that living tissue is inherently electrical, and that the metals are simply conducting this biological electricity from one part of the tissue to another. He publishes his findings in 1791 in a paper called De Viribus Electricitatis in Motu Musculari Commentarius, commentary on the force of electricity in muscular motion. And it causes a sensation. People across Europe start replicating his experiments. Frog legs are twitching in laboratories from London to St. Petersburg. Galvani becomes famous. Animal electricity is the hot topic in natural philosophy. But here's the thing. Not everyone is convinced. And the most important skeptic lives just a short distance away, in the city of Pavia. His name is Alessandro Volta, and he's a professor of experimental physics, and he thinks Galvani has gotten the explanation completely wrong. Volta respects Galvani. They're cordial, at least at first. But Volta looks at those experiments and sees something Galvani missed. Volta notices that the twitching only happens when two different metals are involved: brass hooks and iron railings, a steel scalpel and a tin plate. Whenever Galvani gets his dramatic results, there are always two dissimilar metals in the circuit, with the wet, salty tissue of the frog leg sitting between them. And Volta starts to suspect that the electricity isn't coming from the frog at all. The frog is just a very sensitive detector, a biological galvanometer, if you will. The real source of the electricity, Volta argues, is the contact between the two different metals, with the moist tissue serving as a conductor between them. This kicks off one of the great scientific rivalries of the 18th century. Galvani and Volta go back and forth, publishing papers, refining experiments, each trying to prove the other wrong. And honestly, they're both partly right, in a way that wouldn't become fully clear for decades. Galvani is correct that biological tissue does generate electrical signals. Your nerves are firing tiny electrical impulses right now as you listen to this. But Volta is correct that the twitching in those specific experiments is caused by the metals, not the frog. The frog leg is just completing the circuit and reacting to the current flowing through it. But Volta doesn't stop at just arguing. He decides to prove his point in the most dramatic way possible. If the electricity comes from the contact between two different metals separated by a moist conductor, then he should be able to produce electricity without any animal tissue at all. He should be able to build a device, a purely artificial device, that generates a steady electrical current. And in the year 1800, that's exactly what he does. Picture this. Volta takes a disc of zinc and a disc of copper, each may be the size of a large coin. He places a piece of cardboard between them, cardboard that's been soaked in brine, in salt water. Then he stacks another zinc disc on top, another piece of wet cardboard, another copper disc, and he keeps going. Zinc, wet cardboard, copper. Zinc, wet cardboard, copper. He builds a tower, a column of these alternating discs, sometimes 30 or 40 pairs high. And when he touches a wire to the bottom of the stack and another wire to the top, he feels a shock. Not a static spark, not a brief crackle like you'd get from rubbing amber on fur. A continuous, steady flow of electricity. For the first time in human history, someone has created a reliable, sustained source of electrical current. Volta calls it his artificial electric organ, a reference to the electric eel, but the world quickly starts calling it something else, the voltaic pile. And it changes everything. Think about what existed before this moment. People had static electricity. You could rub things together and get sparks. They had Leyden jars, which were early capacitors that could store a static charge and release it all at once in a single jolt. But nobody had a way to produce a continuous, controllable flow of current. That's what the voltaic pile provides. It's not just a novelty, it's a tool, and it's the very first battery. Now, Volta didn't fully understand why his pile worked. He believed the electricity was generated purely by the contact between the two metals, and that the wet cardboard was just a conductor. He didn't realize that chemical reactions were taking place, that the zinc was actually dissolving, slowly being eaten away, and that this chemical change was what liberated the electrical energy. That deeper understanding would come later, but the device itself worked, and it worked well enough to electrify, quite literally, the entire scientific community. Volta announced his invention in a letter to Sir Joseph Banks, the president of the Royal Society in London, in March of 1800. The letter was read aloud at a meeting of the Society, and within weeks, scientists across Europe were building their own voltaic piles. The impact was immediate and profound. Here's why this mattered so much, and I want you to really sit with this for a moment. Before the voltaic pile, electricity was essentially a curiosity. It was something you demonstrated at parties, something you studied in philosophical terms. You could make sparks and shocks, but you couldn't do sustained work with it. The voltaic pile changed electricity from a phenomenon into a resource. It gave scientists a river of current they could direct, control, and experiment with. And within months, literally months, of Volta's announcement, that river of current started revealing secrets that had been hidden since the beginning of time. One of the first and most dramatic demonstrations came from two British chemists, William Nicholson and Anthony Carlisle. Just weeks after learning about Volta's pile, they built one of their own and used it to pass current through water. And the water decomposed. It split apart into its constituent elements, hydrogen gas bubbling up at one electrode, oxygen gas at the other. This was electrolysis, and it was the first direct proof that water was not an element, but a compound, made of simpler substances held together by what turned out to be electrical forces. That's a staggering insight, and it came directly from having a battery. A few years later, a young Humphrey Davy at the Royal Institution in London took this even further. Davy was brilliant, charismatic, the kind of scientist who could fill a lecture hall. People actually bought tickets to watch him do experiments. And Davy realized that if electricity could break water apart, maybe it could break apart other substances too. Substances that had resisted every other method of decomposition. He built enormous voltaic piles, some with hundreds of pairs of plates, and he used the current to tear apart compounds that no one had ever been able to decompose before. In 1807 and 1808, Davy isolated a string of new elements: potassium, sodium, calcium, barium, strontium, magnesium, elements that had been locked inside minerals and salts since the earth formed, elements that no human being had ever seen in their pure state. When he first isolated potassium by passing current through molten potash, the tiny globules of pure metal that formed were so reactive, they burst into flame on contact with air. Davy reportedly danced around the laboratory with joy. He was in his late 20s. And all of this, the electrolysis, the new elements, the revolution in chemistry, all of it traces back to that stack of zinc and copper discs with wet cardboard in between. That's the thing about batteries that I find so compelling. They're not just devices, they're enablers. They unlocked entire fields of science that couldn't have existed without them. But let's come back to the pile itself for a moment, because as revolutionary as it was, the voltaic pile had real problems. Serious, practical problems that became apparent almost immediately. For one thing, it was fragile. You've got this tall stack of metal discs and soggy cardboard, and if it tips over, you're done. The cardboard dries out, the salt water leaks, the zinc corrodes unevenly. The voltage drops off pretty quickly as you use it. And there's another issue that Volta himself noticed but couldn't explain. If you short-circuit the pile, if you connect the two ends directly with a thick wire, the current is strong at first, but fades rapidly. Something is being used up inside the pile, and Volta, who believed the electricity came from metal-to-metal contact rather than chemistry, couldn't account for this. So almost immediately, people started trying to improve on Volta's design. And one of the first significant improvements came from a man you might not have heard of, but whose contribution was enormous. His name was William Cruikshank, a British chemist, and sometime around 1800 or 1801, he built what's called the trough battery. Instead of stacking discs vertically, Cruikshank laid pairs of zinc and copper plates side by side in a long wooden trough, like books on a shelf, and filled the trough with brine or dilute acid. This solved the leaking problem. It was much more stable, and it was easier to build at large scales. It was, in a sense, the first practical battery design. The first one you could actually use reliably in a laboratory without it falling apart. But the fundamental limitations remained. These early batteries all suffered from what we'd now call polarization, a buildup of hydrogen gas bubbles on the copper electrode that insulated it from the liquid and choked off the current. They also suffered from something called local action, where impurities in the zinc caused it to dissolve even when the battery wasn't being used, wasting the zinc for no useful purpose. These were real engineering problems, and solving them would take decades of patient, incremental work by dozens of researchers across Europe. And one of the most important figures in that next chapter of the story was a quiet, methodical Englishman named John Frederick Daniell, who in 1836 came up with an idea so clever, so elegantly simple, that it would keep batteries useful and reliable for the next half-century. Daniell was a professor of chemistry at King's College London, and he'd been frustrated by the same problems everyone else had noticed: the rapid decline in current, the bubbles, the inconsistency. And his solution involved something that might seem obvious in hindsight, but was genuinely ingenious at the time. He decided to separate the two halves of the chemical reaction into two different containers, connected by a porous barrier that would let ions pass through, but keep the liquids from mixing freely. On one side, a zinc electrode sitting in sulfuric acid. On the other side, a copper electrode sitting in a solution of copper sulfate. In between them, an unglazed earthenware pot that acted as a kind of selective membrane. The beauty of the Daniell cell was that instead of hydrogen bubbles forming on the copper plate, which was the whole polarization problem, the copper ions in the copper sulfate solution would accept the electrons instead, plating out as fresh metallic copper on the electrode. No bubbles, no polarization. A steady, reliable voltage of about 1.1 volts that could last 4 hours. It was the first truly dependable battery, and it became the standard power source for telegraph systems across Europe and North America. And that's a detail worth lingering on for a moment, because the telegraph was the internet of the 19th century. It was the first technology that let human beings send information faster than a horse could carry it. And the Daniell cell was what made it practical. Before Daniell's design, you couldn't trust a battery to deliver a steady signal over the hours and hours that a telegraph office needed to operate. The voltage would sag, the current would weaken, and your dots and dashes would turn to mush on the receiving end. But with the Daniell cell, you had something you could count on. You could wire up a telegraph line from London to Birmingham, sit an operator at each end, and know that the battery powering the whole thing would behave itself for a full working day. That reliability changed everything. It turned the telegraph from a laboratory curiosity into a commercial technology, and it turned batteries from scientific instruments into industrial tools. Now, the Daniell cell wasn't perfect. It was heavy. It was fragile. You've got earthenware pots and open containers of acid after all, and you had to maintain it. The copper sulfate solution would gradually get weaker as copper plated out, and you'd need to top it up. The zinc would slowly dissolve and eventually need replacing. But compared to what came before, it was a revelation, and it established a principle that would echo through every battery design that followed. If you want a reliable cell, you need to manage the chemistry carefully, keep the reactions separated and controlled, and think about what's happening at each electrode independently. Here's the thing about the mid-1800s, though. Once Daniell showed that you could dramatically improve battery performance by rethinking the chemistry, it was like he'd opened a door and a whole crowd of inventors rushed through it. The decades after 1836 saw an explosion of new battery designs, each one trying to solve a slightly different problem or optimize for a slightly different use case. And the names of these batteries read like a who's who of 19th-century chemistry. You've got the Grove cell, the Bunsen cell, the Leclanché cell, the Clark cell, the Weston cell, each one associated with a specific person who had a specific insight about how to make electrons flow more reliably, more powerfully, or more cheaply. Let's talk about William Robert Grove for a second, because his story is fascinating. Grove was a Welsh judge, an actual practicing lawyer and later a judge, who did chemistry essentially as a serious hobby. And in 1839, just 3 years after Daniell's breakthrough, Grove came up with a cell that used platinum and zinc, with nitric acid on one side and sulfuric acid on the other. The Grove cell produced about 1.8 volts, which was significantly more than the Daniell cell's 1.1 volts, and it could deliver more current too. It became the preferred battery for the American telegraph system for a while, because that extra voltage meant you could push a signal down a longer wire. But it had a nasty drawback. The nitric acid gave off toxic brown fumes of nitrogen dioxide. Imagine sitting in a telegraph office all day with that wafting up from the battery room in the basement. Not ideal. And here's a wonderful tangent about Grove. That same year, 1839, he also did something that wouldn't be fully appreciated for over a century. He ran his battery chemistry backward. He took 2 platinum electrodes, exposed one to hydrogen gas and the other to oxygen gas, immersed them in sulfuric acid, and showed that you could generate electricity directly from the chemical combination of hydrogen and oxygen. He called it a gas voltaic battery. We call it a fuel cell. Grove invented the fuel cell in 1839, and then the world basically forgot about it for 120 years, until the space program needed a lightweight power source. But that's a story for later. Robert Bunsen, yes, the Bunsen burner Bunsen, modified Grove's design in 1841 by replacing the expensive platinum electrode with a rod of compressed carbon. Same basic chemistry, same nitric acid fumes, but dramatically cheaper. The Bunsen cell became widely used in laboratories and for electroplating, which was a booming industry at the time. People wanted silver-plated cutlery and gold-plated jewelry, and you needed a battery that could deliver a lot of current to deposit metal onto a surface. The Bunsen cell could do that affordably. But here's what I want you to notice about this whole period. Every one of these batteries was what we call a primary cell. You used it until the chemicals were exhausted, and then it was done. You couldn't recharge it. The zinc dissolved, the acid got used up, and you either rebuilt the cell with fresh materials or threw it away. That's a fundamental limitation, right? It means your battery is essentially a very slow, very expensive way of converting zinc into electricity. And zinc isn't free. For laboratory work or telegraph offices, where you had technicians maintaining the equipment, that was manageable. But it meant batteries couldn't scale to bigger applications. You couldn't run a factory on primary cells. You couldn't power a city. The cost would be astronomical. So the question that was quietly simmering in the background through all of this was, can you make a battery that runs backward? Can you push electricity into it and reverse the chemical reaction, restoring the original materials so you can discharge it again? A rechargeable battery, a secondary cell. And the answer turned out to be yes, but it took a very different kind of chemistry to make it work. The person who figured this out was a French physicist named Gaston Planté, and his story doesn't get nearly enough attention. Planté was working in Paris in the late 1850s, and he was experimenting with lead electrodes and sulfuric acid. Now, lead is a curious metal. It's soft, it's heavy, it's toxic, and it corrodes in interesting ways. When you put 2 lead plates in sulfuric acid and pass a current through them, something remarkable happens. One plate develops a coating of lead dioxide. That's lead combined with oxygen. And the other plate stays as pure lead, but its surface gets roughened and activated. And when you disconnect the charging source and connect the 2 plates to each other through an external circuit, current flows. The lead dioxide reacts with the sulfuric acid and the pure lead. Both plates gradually convert to lead sulfate, and you get a steady flow of electrons. Here's the beautiful part. When the battery is exhausted and both plates are coated in lead sulfate, you can reverse the whole process. Push current back through in the opposite direction, and the lead sulfate converts back to lead dioxide on one plate and pure lead on the other. The sulfuric acid is regenerated, and you're right back where you started, ready to discharge again. Planté demonstrated this in 1859, and it was the first rechargeable battery in history. We still call it the lead-acid battery, and if that name sounds familiar, it should. It's the same basic chemistry that starts your car every morning. Think about that. The fundamental design is over 160 years old, and it's still under the hood of essentially every car with an internal combustion engine on the planet. That's an extraordinary run for any technology. Now, Planté's original batteries were weak. the lead plates were smooth, which meant the surface area where the chemistry could happen was small, which meant the capacity was low. He improved them by a tedious process he called forming, repeatedly charging and discharging the plates over months, which gradually roughened the surface and built up thicker layers of active material. It worked, but it was painfully slow. And for about 20 years, the lead-acid battery remained a laboratory curiosity because nobody could figure out how to manufacture them efficiently. The breakthrough came from Camille Alphonse Faure, another Frenchman who in 1881 had the simple but transformative idea of pasting the lead plates with a mixture of lead oxides before assembling the battery. Instead of waiting months for the forming process to build up active material naturally, you could just smear it on. This massively increased the surface area and the capacity of the cells right from the start. Faure's improvement turned the lead-acid battery from a lab curiosity into a practical commercial product almost overnight. And the timing was perfect because something else was happening in 1881 that would create enormous demand for rechargeable batteries. Electrical power generation was taking off. Edison was building his Pearl Street station in New York. Swan and Edison were both commercializing the incandescent light bulb. Suddenly, there were power stations generating electricity, and people wanted to store it. The lead-acid battery was the only technology that could do that. Electric utilities used massive banks of lead-acid cells to smooth out demand, charging them when the generators had excess capacity and discharging them during peak hours. Electric vehicles, believe it or not, were hugely popular in the 1890s and early 1900s, and they all ran on lead-acid batteries. There was a brief, fascinating period when it genuinely wasn't clear whether the future of the automobile would be electric, steam, or gasoline. In 1900, about a third of all cars on American roads were electric. They were quiet. They were clean. They were easy to drive. No hand cranking. No gear shifting. The Baker Electric, the Detroit Electric, the Columbia. These were real, popular cars, and every single one of them was powered by Planté and Faure's chemistry, lead and sulfuric acid, doing their quiet electrochemical dance under the floorboards. So, what happened? Why did gasoline win? Well, it's a complicated story involving Henry Ford and mass production and the discovery of cheap Texas oil. But from a battery perspective, the answer comes down to one concept that we need to talk about, because it's absolutely central to understanding why some batteries succeed and others don't. It's called energy density, and it's probably the single most important number in all of battery engineering. Energy density tells you how much energy you can pack into a given amount of weight or a given amount of space. And those are actually two slightly different measurements. Gravimetric energy density, which is energy per unit of mass, usually measured in watt-hours per kilogram, and volumetric energy density, which is energy per unit of volume, measured in watt-hours per liter. Both matter, but for vehicles, it's the weight one that really kills you. So, let's focus there. Here's a way to think about it. Imagine you've got a kilogram of gasoline, just a little over 2 pounds. That kilogram contains roughly 12,000 watt-hours of chemical energy. 12,000. Now, a kilogram of lead-acid battery, fully charged, contains about 30 to 40 watt-hours. you see the problem. Even if you account for the fact that an internal combustion engine wastes most of its energy as heat, and it does, it's only maybe 20 to 25% efficient, you're still getting something like 2,000 to 3,000 usable watt-hours per kilogram of gasoline, compared to 30 or 40 from lead acid. That's a factor of nearly 100. 100 times more usable energy per kilogram. Think about what that means for a car. To get the same driving range as a gasoline vehicle, an electric car in 1900 would need a battery pack that weighed roughly 100 times more than the equivalent gasoline tank. That's not a slight disadvantage. That's a fundamental, structural, almost insurmountable gap. And it's why those beautiful, quiet Baker Electrics had a range of maybe 50 to 100 miles on a good day, with a top speed around 25 miles per hour, while a gasoline car could go farther, go faster, and refuel in minutes instead of hours. The moment Henry Ford figured out how to make gasoline cars cheap with his assembly line starting around 1908, and especially after the electric starter motor eliminated the dangerous hand crank in 1904. Invention, by the way, for Cadillac. The electric car was essentially doomed, not because the idea was bad, but because the battery chemistry couldn't compete with the energy density of liquid hydrocarbons. And honestly, that gap has defined battery research for over a century. Every major advance in battery technology since then has been, in one way or another, an attempt to close that gap, to pack more energy into less weight. Now, here's what's interesting. Even though lead acid lost the car race, it didn't disappear. Far from it. Remember, energy density isn't the only thing that matters. For applications where weight isn't the main concern, where you need something reliable, something cheap, something that can deliver big bursts of current, lead acid is fantastic. And that's exactly why when Kettering designed that electric starter motor for the 1912 Cadillac, guess what battery he used to power it? Lead acid. The same chemistry that couldn't compete with gasoline for propulsion found its perfect niche starting the gasoline engine. And it's still there. If you drive a car with a conventional engine, you've got a lead acid battery under your hood right now, doing essentially the same job it did in 1912. Over 100 years of continuous service in the same application. That's a remarkable run for any technology. But let's leave lead acid sitting comfortably in its niche for a moment, because while all of this automotive drama was playing out, something else was happening in battery chemistry that would turn out to be enormously important. And it starts with a Swedish inventor named Waldemar Jungner. Jungner was working in the 1890s, right in the thick of that electric vehicle era, and he was frustrated by the same limitations everyone else saw in lead-acid batteries. They were heavy. The sulfuric acid was corrosive and dangerous. The lead plates were fragile if you discharged them too deeply. He wanted something better. And in 1899, he patented a rechargeable battery that used completely different chemistry, nickel and cadmium, with an alkaline electrolyte of potassium hydroxide instead of acid. The nickel-cadmium battery. You might know it as NiCad. Now, here's the thing about Jungner's nickel-cadmium cell. It wasn't dramatically better than lead acid in terms of energy density. It was somewhat better, maybe 45 to 50 watt-hours per kilogram, compared to lead acid's 30 to 40. A modest improvement. But it had other advantages that were genuinely significant. The alkaline electrolyte didn't eat through things the way sulfuric acid did. The battery was much more mechanically robust. You could shake it, vibrate it, mount it in any orientation. And, crucially, you could abuse it electrically in ways that would destroy a lead-acid cell. You could discharge it almost completely, and it would bounce right back. You could overcharge it a bit without catastrophic consequences. It was, in a word, tough. But nickel-cadmium had a problem of its own, and it was economic. Cadmium was expensive. Nickel wasn't cheap either. And Youngner's manufacturing process was complicated. So for decades, nickel-cadmium batteries remained a specialty product, used in applications where ruggedness mattered more than cost. Military equipment, aircraft, railroad signaling, places where you absolutely could not afford a battery failure, and you were willing to pay a premium for reliability. Now, here's where the story gets a little bit tangled, because working at almost exactly the same time as Youngner, just across the Atlantic, was Thomas Edison. And Edison was working on a very similar idea, a rechargeable alkaline battery, but with a different twist. Instead of nickel and cadmium, Edison used nickel and iron. He patented his nickel-iron battery in 1901, and he had grand ambitions for it. Edison specifically wanted to build a better battery for electric vehicles. He looked at lead-acid, saw all its weaknesses, and believed he could create something superior. And in some ways, he did. The nickel-iron battery was incredibly durable, almost unkillable, really. You could leave it discharged for years, come back, charge it up, and it would work fine. The alkaline electrolyte didn't corrode the way acid did. Some nickel-iron batteries from Edison's era have been found still functional after 80 or 90 years. That's not a typo. 80 to 90 years. In terms of sheer longevity, nothing else comes close. But Edison's battery had a fatal flaw for the application he cared about most. It was inefficient. When you charged it, a significant portion of the electrical energy, something like 20 to 25%, was wasted as heat. The nickel-iron chemistry just wasn't very efficient at converting electrical energy to chemical energy and back again. And it had high self-discharge, meaning it would slowly lose its charge just sitting there. For an electric vehicle, where every watt-hour matters, this was devastating. Edison spent nearly a decade trying to improve it, pouring enormous resources into the project. He reportedly enraged his investors with the delays. At one point, he recalled every battery he'd sold and started over from scratch. When he finally released his improved version around 1910, it was genuinely better. But by then, Ford's Model T had already won the market. The gasoline car had triumphed, and Edison's dream of an electric vehicle battery was, for the moment, dead. There's a wonderful irony here, by the way. Edison and Ford were close friends, genuinely close. They went on camping trips together. Their families vacationed together. And Ford actually drove a Detroit electric car that Edison had fitted with his nickel-iron batteries. But Ford's own company was mass-producing gasoline cars that were making electric vehicles obsolete. It's one of those strange contradictions of history. So by the early 20th century, we've got this landscape of battery chemistries. Lead-acid for starting engines and storing grid power. Nickel-cadmium for military and specialty applications. Nickel-iron as Edison's tough but inefficient creation, finding a niche in industrial applications, like mining equipment and railroad cars, where its extraordinary durability outweighed its inefficiency. And then the whole universe of primary cells, non-rechargeable batteries, which were evolving in their own direction for flashlights and radios and all the portable devices that were starting to appear. Let's talk about those primary cells for a moment, because something important was happening there. The old Leclanché cell. That was Georges Leclanché's 1866 invention, a zinc and manganese dioxide cell with an ammonium chloride paste electrolyte, had evolved into what we now call the zinc-carbon battery. You've seen these. If you've ever bought the cheapest batteries at the store, the ones that come in a big value pack, those are essentially Leclanché's chemistry, refined and miniaturized. They're not great by modern standards, but they're incredibly cheap, and for over a century, they were the default portable power source for the world. But in the 1950s, a Canadian engineer named Louis Urey, working for the Eveready Battery Company, which you probably know as Energizer, made a breakthrough that seems simple in retrospect, but changed everyday life for billions of people. Urey replaced the ammonium chloride electrolyte in the zinc-carbon cell with potassium hydroxide, an alkaline electrolyte. He also used powdered zinc instead of a solid zinc casing, which gave much more surface area for the chemical reaction. The result was the alkaline battery, and it was dramatically better than zinc-carbon. It lasted longer, it performed better under heavy loads, it worked better in cold weather, and it had a longer shelf life. Urey demonstrated his prototype by putting it in a toy car and racing it against a car powered by regular zinc-carbon batteries. His alkaline-powered car was still running long after the other one had stopped. Eveready began selling alkaline batteries commercially in 1959, and they gradually took over the consumer market. When you buy a pack of AA or AAA batteries today, you're almost certainly buying alkaline cells. Urey's basic chemistry, refined and optimized over decades, but fundamentally the same idea. Zinc and manganese dioxide with a potassium hydroxide electrolyte. It's one of those inventions that's so ubiquitous, so woven into everyday life, that we forget someone had to actually figure it out. But here's the thing about all of these batteries. The lead acid, the nickel cadmium, the nickel iron, the alkaline, they all share a common characteristic that would eventually become a serious limitation. They're all aqueous systems, meaning their electrolytes are water-based solutions. And water has a fundamental electrochemical constraint that puts a ceiling on how much voltage you can get from a single cell. Water molecules start to break apart, they electrolyze, at about 1.23 volts. In practice, you can push a bit beyond that because of something called overpotential, which is why a lead acid cell gives you about 2 volts and a nickel cadmium cell gives you about 1.2 volts. But you can't push much further. The water itself becomes the limiting factor. Now, voltage matters enormously for energy density because the energy stored in a battery is essentially voltage times capacity. If you could find a way to get higher voltage per cell, you could store more energy in the same amount of material. And to get higher voltage, you'd need to abandon water-based electrolytes entirely and find something that could tolerate a much wider voltage window without breaking down. That realization that the path to truly high energy density ran through non-aqueous electrolytes would lead researchers toward an element that, at first glance, seems almost absurdly dangerous to put inside a battery. It's the lightest metal on the periodic table. It's so reactive that it bursts into flame on contact with water, and it would eventually change everything. Lithium. Element number 3. Just 3 protons in its nucleus, 3 electrons orbiting around them. It sits at the very top of the alkaline metal group on the periodic table, right above sodium and potassium. And it's the lightest solid element there is. If you held a chunk of pure lithium in your hand, which you really shouldn't do, by the way, you'd be surprised by how light it feels. It's about half the density of water. You could float it on oil. It's soft enough to cut with a butter knife, silvery when freshly sliced, and it tarnishes almost instantly in air. And if you dropped it into a glass of water, it would fizz and skitter across the surface, reacting violently, generating hydrogen gas and heat, and if conditions were right, that hydrogen could ignite. Lithium desperately wants to give away its outermost electron. That's what makes it so reactive, and that's also what makes it so extraordinarily interesting for batteries. Think about what that means from an electrochemical perspective. A battery works because one material wants to give up electrons, and another material wants to accept them, and you force those electrons to travel through an external circuit to get from one to the other. The more desperately the anode material wants to shed electrons, and the more eagerly the cathode material wants to grab them, the higher the voltage you get. Lithium has the most negative standard electrode potential of any metal, about negative 3.04 volts against a standard hydrogen electrode. That's enormous. It means a lithium anode paired with the right cathode could theoretically produce cells with voltages of 3 volts, 4 volts, maybe even higher. Compare that to the 1.2 volts of a nickel-cadmium cell, or the 1.5 volts of an alkaline cell. You're talking about potentially tripling or quadrupling the voltage per cell. And because lithium is so light, just 6.94 grams per mole, the lightest metal there is, you get all that electrochemical punch with almost no weight penalty. The theoretical energy density is staggering. So researchers in the 1960s and 1970s started asking the obvious question, can we actually build a battery with lithium? And the answer was yes, but it was incredibly hard. And the journey from this should work in theory to this is a product you can buy would take decades and involve some genuinely dramatic twists. The first challenge was the electrolyte. You obviously can't use water. Lithium and water are a violent combination, and besides, the whole point is to escape that voltage ceiling that water imposes. So, you need a non-aqueous electrolyte, something that can conduct lithium ions between the electrodes without reacting with the lithium itself. Early researchers explored organic solvents, things like propylene carbonate, mixed with lithium salts that could dissolve and provide mobile ions. These organic electrolytes could tolerate much higher voltages without breaking down, which was exactly what you needed. But they came with their own problems. They were flammable. They were less conductive than aqueous solutions, meaning the internal resistance of the cell was higher, and getting them to work reliably without side reactions slowly degrading the battery was a real puzzle. The first commercial lithium primary cells, non-rechargeable ones, started appearing in the 1970s. These used a lithium metal anode and various cathode materials. One early chemistry paired lithium with sulfur dioxide, and another used lithium with thionyl chloride. These cells were remarkable. They could deliver 3 volts or more from a single cell. They had fantastic shelf life because lithium forms a thin protective layer on its surface that slows self-discharge, and they packed way more energy per kilogram than anything that came before. The military loved them. They went into radios, sensors, emergency equipment, anywhere you needed a lot of energy in a small, light package and didn't need to recharge it. Some of those lithium primary chemistries are still used today. That little coin cell in your watch, the CR2032. The CR stands for lithium manganese dioxide chemistry. It's a lithium primary cell, and it's been powering watches, calculators, car key fobs, and motherboard clocks for decades. But the real prize was a rechargeable lithium battery. And here's where the story gets fascinating, because making lithium rechargeable turned out to be one of the hardest problems in materials science, and solving it required a conceptual breakthrough that nobody saw coming. The problem with recharging a lithium metal battery is what happens to the lithium when you try to plate it back onto the anode during charging. In a lead-acid battery, when you recharge it, the lead reforms relatively smoothly on the electrode surface. Lithium doesn't do that. When lithium ions from the electrolyte deposit back onto a lithium metal surface, they tend to form dendrites, tiny, needle-like growths that branch out irregularly, like frost crystals growing on a window pane. These dendrites are a nightmare. They increase the surface area of the lithium, which accelerates unwanted side reactions with the electrolyte. Worse, they can grow long enough to physically bridge the gap between the anode and cathode, creating an internal short circuit. And when a lithium cell short circuits internally, with all that flammable organic electrolyte around, the result can be thermal runaway, a rapid, self-sustaining increase in temperature that can lead to fire or even explosion. Early rechargeable lithium metal cells had a disturbing tendency to catch fire. This wasn't a minor engineering hiccup. It was a fundamental materials problem, and for a while, it looked like it might be a dead end. The breakthrough came from an unexpected direction, and it involved a concept so elegant that it would eventually earn its key architects the Nobel Prize in chemistry. The idea was this: what if you didn't use lithium metal at all? What if, instead of having a chunk of lithium that dissolves and replates during cycling, you used materials that could absorb and release lithium ions into their crystal structure, like a sponge soaking up and squeezing out water? If both electrodes were made of materials with open, layered structures that lithium ions could slide in and out of, then you'd never have free lithium metal in the cell. No lithium metal, no dendrites. No dendrites, no short circuits. No short circuits, no fires. The lithium would exist only as ions, shuttling back and forth between the two electrodes through the electrolyte. This concept became known as the rocking chair battery, or, more formally, the lithium-ion battery. The lithium ions rock back and forth between the two electrodes, and the electrons follow through the external circuit. It's beautiful in its simplicity. Now, the people who made this work, there are 3 names you should know, and their stories intertwine in interesting ways. The first is Stanley Whittingham, a British-American chemist working at Exxon, of all places, in the 1970s. Yes, the oil company. Exxon was actually doing serious battery research during the energy crisis, hedging their bets on future energy technologies. Whittingham discovered that lithium ions could intercalate, that's the technical term, for reversibly inserting themselves into the layered crystal structure of titanium disulfide. He built a working, rechargeable cell with a lithium metal anode and a titanium disulfide cathode, and it worked. Lithium ions would slide between the layers of the titanium disulfide when the battery discharged, and slide back out when it charged. This was around 1976, and it was a genuine proof of concept, but it still used a lithium metal anode, so the dendrite problem remained, and titanium disulfide was expensive. Exxon eventually shelved the project. The second name is John Goodenough, and his story is one of the most remarkable in the history of science. Goodenough was already in his mid-50s when he made his most important contribution, working at Oxford University. In 1980, he and his collaborators demonstrated that lithium cobalt oxide, LiCOO2, could serve as a cathode material and produce a significantly higher voltage than Whittingham's titanium disulfide. We're talking about 4 volts per cell, compared to about 2 volts. That nearly doubled the energy density. Goodenough had essentially identified the cathode material that would power the mobile electronics revolution. And here's what's remarkable about the man. He didn't patent it in a way that made him wealthy. Oxford didn't initially see the commercial potential. The discovery was published, shared with the world, and others would build on it. Goodenough kept working, kept pushing, kept contributing to battery science for decades. He won the Nobel Prize in 2019 at the age of 97, making him the oldest Nobel laureate in history. He passed away in 2023 at 100 years old, still affiliated with the University of Texas at Austin, still thinking about batteries. The third name is Akira Yoshino, a Japanese chemist working at Asahi Kasei Corporation. And Yoshino is the one who solved the anode problem. In 1985, he demonstrated that you could replace the lithium metal anode with a carbon-based material, specifically a form of petroleum coke and later graphite, that could also intercalate lithium ions. Graphite has a layered structure, sheets of carbon atoms arranged in hexagonal rings, stacked on top of each other, and lithium ions can slip between those layers and nestle in there quite comfortably. So now you had a cell where both electrodes were intercalation hosts. The cathode was lithium cobalt oxide, the anode was carbon, and lithium ions rocked back and forth between them through a non-aqueous electrolyte. No lithium metal anywhere in the cell during normal operation. Yoshino built prototype cells and showed they were safe, stable, and rechargeable over many cycles. This was the configuration that changed the world, but it still needed someone to actually manufacture it at scale, to take it from a laboratory curiosity to a product. And that someone was Sony. In 1991, Sony commercialized the first lithium-ion battery using Goodenough's lithium cobalt oxide cathode and Yoshino's carbon anode design. They put it in a camcorder, the CCD-TR1, and it was a revelation. The battery was lighter, lasted longer, and delivered higher voltage than anything else on the market. It was 3.6 volts per cell compared to 1.2 for the nickel-cadmium cells it replaced. Think about what that means practically. Where you used to need 3 nickel-cadmium cells in series to get 3.6 volts, you now needed just 1 lithium-ion cell. Fewer cells, less weight, simpler design. And the timing was extraordinary. The early 1990s were exactly when portable electronics were about to explode. Laptops were getting smaller. Mobile phones were shrinking from bricks to something you could actually carry in a pocket. Personal digital assistants, portable CD players, digital cameras, all of these devices were hungry for energy-dense, lightweight, rechargeable batteries. Lithium-ion arrived at precisely the moment the world needed it most, and the two technologies, portable electronics and lithium-ion batteries, drove each other forward in a virtuous cycle. Better batteries enabled smaller, more capable devices. The massive demand for those devices funded further battery research and manufacturing scale-up, which brought costs down and performance up, which enabled even more devices. But let's slow down for a moment and actually understand what's happening inside a lithium-ion cell, because the mechanism is genuinely elegant. Picture the cell as two bookshelf-like structures facing each other across a room filled with a special liquid. One bookshelf is made of graphite, layers of carbon, and the other is made of lithium cobalt oxide, layers of cobalt and oxygen, with lithium tucked between them. When the battery is fully charged, the lithium ions are all nestled between the layers of the graphite anode. The cell is tense with stored energy, like a compressed spring. When you connect a device and start drawing power, those lithium ions slip out from between the graphite layers, dissolve into the electrolyte, drift across to the cathode side, and tuck themselves between the layers of the lithium cobalt oxide. For every lithium ion that makes that journey through the electrolyte inside the cell, one electron makes the same journey through the external circuit, through your phone, your laptop, your whatever, doing useful work along the way. When you plug in the charger, you reverse the process. You push electrons back the other way, and the lithium ions obediently migrate back to the graphite anode and slide between the carbon layers. Again, ready for the next discharge. The electrolyte in the middle is typically a lithium salt. Lithium hexafluorophosphate is a common one, dissolved in a mixture of organic carbonates. And between the two electrodes, there's a thin polymer separator, a membrane with microscopic pores that allows lithium ions to pass through, but keeps the electrodes from physically touching each other. That separator is critical. If it fails, if something punctures it, or it melts from overheating, the electrodes can touch. You get a short circuit, and things can go very wrong very quickly. We'll come back to that, because the safety story of lithium-ion batteries is its own dramatic chapter, full of burning laptops and grounded airplanes, and engineers scrambling to figure out what went wrong. So let's get into it, because it's a story that shaped the entire trajectory of the technology. The thing you have to appreciate first is just how much energy is packed into a lithium-ion cell. That's the whole point. That's why we use them. But energy density is a double-edged sword. The same chemistry that lets you run a laptop for 8 hours or drive a car 300 miles also means that if something goes wrong inside the cell, there's a lot of energy available to fuel a very bad outcome. And the organic carbonate electrolyte, that liquid the lithium ions swim through, is flammable, not a little flammable, genuinely, seriously flammable. So you've got a high-energy electrochemical system sitting in a bath of flammable solvent, separated by a membrane thinner than a human hair. When everything works correctly, it's perfectly safe. Billions of these cells operate every day without incident. But when things go wrong, they can go wrong fast. The failure mode engineers worry about most is called thermal runaway. Here's what happens. If something causes a short circuit inside the cell, maybe a manufacturing defect left a tiny metallic particle on the electrode, maybe the cell got punctured, maybe it was overcharged, and lithium metal started plating on the anode, forming those dendrites we talked about earlier. Whatever the cause, you get a spot where current flows where it shouldn't. That spot heats up. As it heats up, it triggers exothermic chemical reactions inside the cell. Those reactions generate more heat. More heat triggers more reactions. It's a positive feedback loop, a runaway chain of events where the temperature climbs from normal operating range to hundreds of degrees Celsius in seconds. The electrolyte starts decomposing and releasing flammable gases. The separator melts, which makes the short circuit worse. Eventually, the cell can vent those hot gases, and if they ignite, and they often do, you get fire. In a multi-cell battery pack, one cell going into thermal runaway can heat the cells next to it enough to push them into thermal runaway too. And now, you've got a cascade. It's not an explosion exactly, though it can look like one. It's more of a rapid, intense, self-sustaining chemical fire that's very difficult to put out because the cell is generating its own oxygen from the decomposition of the cathode material. The first really big public wake-up call came in 2006. Dell recalled about 4.1 million laptop batteries made by Sony. There had been incidents, laptops catching fire, sometimes, dramatically, in offices and airports. The root cause turned out to be microscopic metal particles contaminating the cells during manufacturing. Tiny flakes of metal, smaller than a grain of sand, that could eventually work their way through the separator and cause an internal short. Sony ended up recalling roughly 10 million batteries across multiple laptop brands. It was one of the largest consumer electronics recalls in history at that point, costing Sony hundreds of millions of dollars. And it forced the entire industry to get much more serious about quality control in cell manufacturing. The tolerances are extraordinary. A lithium-ion cell factory is essentially a clean room. Humidity has to be controlled because lithium compounds react with moisture. Particle contamination has to be minimized to levels that would impress a semiconductor fab. Every cell has to be tested, cycled, monitored. But manufacturing defects aren't the only risk. Overcharging is dangerous because it can cause lithium metal to plate out on the anode surface. You're pushing more lithium into the graphite than it can hold. So, the excess deposits as metallic lithium, which can form dendrites that pierce the separator. Over-discharging can cause the copper current collector on the anode side to dissolve and later redeposit in ways that create internal shorts. Physical damage, dropping a phone, crushing a cell, can breach the separator mechanically. So every lithium-ion battery you've ever used has a battery management system, a BMS, which is a little electronic brain that monitors voltage, current, and temperature, cell by cell, and prevents overcharging, over-discharging, and excessive current draw. In a phone, it's a small chip. In an electric car, it's a sophisticated computer managing thousands of cells. The BMS is arguably as important as the cells themselves. Without it, lithium-ion batteries would be far too dangerous for consumer use. The most dramatic safety incident in recent memory, the one that really made headlines, was the Boeing 787 Dreamliner. In January 2013, just months after the 787 entered commercial service, a battery caught fire on a Japan Airlines 787 parked at Boston's Logan Airport. The plane was empty, thankfully, but the fire was intense enough to burn through the bottom of the fuselage. 9 days later, an all-Nippon Airways 787 had to make an emergency landing in Japan after a battery started smoking and venting in flight. The entire global fleet of 787s was grounded. The first fleet-wide grounding by the FAA in over 30 years. The 787 used large lithium-ion battery packs for its auxiliary power unit, and the investigation revealed a complex chain of failures, possible internal short circuits, inadequate thermal management, and a battery enclosure that wasn't designed to contain the consequences of thermal runaway. Boeing eventually redesigned the battery system with better cell spacing, improved ventilation, and a stainless steel containment box that could handle a worst-case cell failure without letting fire or fumes reach the rest of the aircraft. The 787 flew again after about 3 months on the ground, but the incident left a lasting mark on how the aviation industry thinks about lithium-ion batteries. And then there was the Samsung Galaxy Note 7 in 2016. Samsung's flagship phone started catching fire in people's pockets, in their hands, on nightstands while charging. Samsung recalled 2.5 million units, issued replacements, and then the replacement phones started catching fire too. The second recall was even more devastating than the first. Airlines banned the phone entirely. You'd hear announcements at the gate specifically telling passengers not to bring a Galaxy Note 7 on board. Samsung's investigation found 2 separate battery defects from 2 different suppliers. One had cells where the negative electrode was deflected in the corner of the casing, and the other had cells with missing or thin insulation tape and sharp protrusions on the welding burrs. It was a brutal lesson. Samsung reportedly lost something like $5 billion, and the whole episode became a case study in how pushing for thinner phones with bigger batteries and faster charging creates an engineering tightrope where the margins for error shrink to almost nothing. Now here's the thing, and this is important to keep in perspective. Despite these incidents, lithium-ion batteries are remarkably safe for what they are. The failure rate is something like 1 in 10 million cells, maybe even lower with modern manufacturing. You carry one in your pocket every day and never think about it. But when you're making billions of cells a year, even a 1 in 10 million failure rate means hundreds of failures, and each one is potentially a fire. So the engineering challenge isn't just making the chemistry work. No, it's making it work safely at massive scale every single time, in cells that are getting thinner, lighter, and more energy dense with every generation. Which brings us to something really important: the evolution of cathode chemistry beyond that original lithium cobalt oxide that Goodenough developed. Because LiCoO2 is a wonderful material in many ways: high voltage, good energy density, relatively easy to manufacture, but it has some significant drawbacks. Cobalt is expensive. It's mined primarily in the Democratic Republic of Congo, often under conditions that raise serious ethical concerns. And from a safety standpoint, lithium cobalt oxide isn't the most thermally stable cathode. It starts releasing oxygen at relatively modest temperatures, which feeds thermal runaway. So researchers spent the 1990s and 2000s developing alternative cathode materials that could address some of these issues. One of the most important was lithium iron phosphate, LiFePO4, often just called LFP. This one came out of Goodenough's lab again, published in 1997 when he was at the University of Texas at Austin. The man just kept contributing. LFP uses iron instead of cobalt, which is cheap, abundant, and ethically uncomplicated, and the phosphate structure is inherently more thermally stable. The oxygen is bound tightly in the phosphate groups and doesn't release easily, which makes LFP cells much more resistant to thermal runaway. The trade-off is lower voltage, about 3.2 volts per cell compared to 3.7 for LiCOO2, and lower energy density. So for years, LFP was seen as the safe but boring option, good for stationary storage and commercial vehicles where you had room for bigger, heavier battery packs, but not ideal for phones or passenger EVs where every watt-hour per kilogram matters. But here's what's interesting, and this is a story that's still unfolding right now. LFP has made a massive comeback. Tesla started putting LFP batteries in its standard range, Model 3, around 2021. Chinese manufacturers like CATL and BYD have pushed LFP technology hard, improving its energy density through better cell-to-pack engineering. Basically, if you make the cells bigger and eliminate wasted space in the pack, you can close the gap with higher energy chemistries at the system level. BYD's Blade battery, introduced in 2020, is an LFP cell shaped like a long, thin blade that serves as a structural element of the pack itself. It's clever engineering that compensates for the chemistry's lower energy density through smarter packaging. Then, there's the NMC family, lithium nickel manganese cobalt oxide. This is where a lot of the action has been for premium EVs and high-performance applications. The idea is to blend nickel, manganese, and cobalt in the cathode in varying ratios to balance energy density, power, longevity, and cost. Early versions used equal parts of each, NMC111, meaning 1 part nickel, 1 part manganese, 1 part cobalt. Over time, the trend has been to push the nickel content higher and reduce the cobalt. NMC532, then NMC622, then NMC811. That last one is 80% nickel, 10% manganese, 10% cobalt. More nickel means more energy density, which means more range for an electric car. But it also means less thermal stability and more sensitivity to manufacturing conditions. It's that same fundamental tension: more energy, more risk, tighter engineering margins. There's also NCA, lithium nickel cobalt aluminum oxide, which is what Panasonic has been making for Tesla's cylindrical cells for years. Very high energy density, which is part of how Tesla achieved industry-leading range numbers. The aluminum is just a small dopant, maybe 5%, but it stabilizes the crystal structure in ways that improve safety and longevity compared to a pure nickel-cobalt cathode. And on the anode side, things have been evolving too, though more quietly. Graphite is still the dominant anode material, the same basic concept Yoshino pioneered in 1985, but there's been a push to add silicon. Silicon can theoretically hold about 10 times more lithium per unit mass than graphite. 10 times. If you could make a pure silicon anode, the energy density gains would be enormous. The problem is that silicon expands by roughly 300% when it absorbs lithium ions. 300%. Imagine a sponge swelling to 4 times its original size every time you charge the battery, then shrinking back when you discharge. That kind of mechanical stress cracks the silicon, breaks the electrical connections, and destroys the cell in just a few cycles. So the approach has been to blend small amounts of silicon, 5%, 10%, into the graphite anode, capturing some of the capacity benefit while keeping the expansion manageable. Every major battery maker is working on increasing that silicon content using nanostructured silicon, silicon oxide composites, clever binder systems that can accommodate the swelling. It's one of the most active areas of battery research right now. But all of these improvements, better cathodes, silicon-enhanced anodes, smarter pack designs, they're incremental. They're pushing the lithium-ion concept further and further, squeezing more energy out of each kilogram, each liter of space. And that raises a question that a lot of very smart people are spending a lot of time on. Is there a next leap? Something beyond lithium-ion that could do for the 21st century what lithium-ion did for the 1990s? Because the demands keep growing. Electric vehicles need cheaper batteries with longer range. Grid-scale storage needs batteries that can absorb solar and wind power and release it hours later, millions of cycles, at rock-bottom cost. And there's a technology that keeps coming up in those conversations. One that loops all the way back to a problem we discussed earlier. The dendrite problem that killed rechargeable lithium metal batteries in the 1980s. The idea is called the solid-state battery, and the concept is deceptively simple. What if you replaced that flammable liquid electrolyte with a solid material that conducts lithium ions just as well, but can't catch fire, and might even be strong enough to physically block dendrites from growing? If you could do that, you could potentially go back to using a pure lithium metal anode. Not graphite, not silicon, but actual metallic lithium, which has a theoretical capacity roughly 10 times higher than graphite. You'd get a cell that's safer and stores dramatically more energy. It sounds almost too good to be true, and in some ways it is, because the challenges are enormous. But the progress over the last decade has been real, and the story behind it is worth telling. So let's think about what a solid-state battery actually looks like, physically. In a conventional lithium-ion cell, you've got your cathode on one side, your anode on the other, and between them, a thin porous separator soaked in liquid electrolyte. That liquid is usually a lithium salt dissolved in an organic solvent, something like lithium hexafluorophosphate in a mix of ethylene carbonate and dimethyl carbonate. It's a good ion conductor, it wets the electrodes nicely, and it works. But it's also flammable, and at high temperatures, it can decompose and generate gas, which is exactly the chain of events we talked about with thermal runaway. In a solid-state cell, you replace all of that, the liquid electrolyte and the separator, with a single solid layer that does both jobs. It conducts lithium ions from one electrode to the other, and it physically separates the cathode from the anode, so electrons can't short circuit through it. That's the whole idea. Simple in concept, incredibly difficult in practice. The first question is, what material do you make this solid electrolyte out of? Because most solids don't conduct ions very well. That's kind of the definition of a solid. The atoms and molecules are locked in place. In a liquid, ions can swim around freely, which is why liquids are naturally good electrolytes. To get a solid that conducts ions, you need a crystal structure or an amorphous matrix that has pathways, channels, essentially, through which lithium ions can hop from site to site. And you need those hops to happen fast enough that the battery can charge and discharge at useful rates. There are three main families of solid electrolytes that researchers have been exploring, and each has its own personality. The first family is oxide-based ceramics. The most famous example is a material called LLZO, lithium lanthanum zirconium oxide, which was first reported around 2007 by a group led by Ramaswamy Murugan and Werner Wepner. LLZO has a garnet crystal structure, and it turns out that structure has these beautiful three-dimensional pathways that lithium ions can move through. The ionic conductivity is decent, not as high as a liquid electrolyte, but in the right ballpark, somewhere around 1/10 of a millisiemens per centimeter at room temperature for the best versions, and it's chemically stable against lithium metal, which is a huge deal. You can press a piece of LLZO against pure lithium, and it doesn't react violently. That's rare. The problem with LLZO and other oxide ceramics is that they're, well, ceramics. They're hard, brittle, and difficult to process. You have to sinter them at very high temperatures, over 1,000 degrees Celsius, to get dense pellets, and even then, getting good contact between the solid electrolyte and the electrode surfaces is really tricky. In a liquid system, the electrolyte naturally fills every pore and crevice, making intimate contact with the active material particles. A rigid ceramic just sits on top. There are gaps, voids, places where ions can't easily transfer. And as the battery cycles and the electrodes expand and contract, even slightly, those contact points can break, and the cell's performance degrades. The second family is sulfide-based solid electrolytes. These are materials like Li6PS5Cl, sometimes called argyridites, or Li10GeP2S12, which goes by the abbreviation LGPS. And here's what's exciting about sulfides. Some of them have ionic conductivities that actually rival liquid electrolytes. LGPS, which was reported by Noriaki Kamaya and colleagues in 2011, clocked in at around 12 millisiemens per centimeter at room temperature. That's remarkable for a solid. It's in the same range as the organic liquid electrolytes used in commercial lithium-ion cells. And sulfides are softer than oxides. They're more mechanically compliant, which means you can cold press them into dense layers without needing those extreme sintering temperatures. That helps with manufacturing. But sulfides have their own headache. They're sensitive to moisture. Expose them to humid air, and they can react to form hydrogen sulfide gas, which is toxic, the rotten egg smell gas. So you have to handle them in dry rooms or argon-filled glove boxes, which adds cost and complexity. they can also be less stable against lithium metal than oxides, and some sulfide compositions react with common cathode materials, requiring protective coatings at the interfaces. The third family is polymer electrolytes, and these actually have the longest history. The idea of using a polymer to conduct lithium ions goes back to work by Peter Wright in the early 1970s and Michel Armand in the late 70s and early 80s. Armand, a French electrochemist who was one of the true visionaries of battery science, recognized that polyethylene oxide, PEO, a common polymer, could dissolve lithium salts and conduct lithium ions through the motion of its polymer chains. The advantage of polymers is that they're flexible, easy to process into thin films, and make good contact with electrodes. The disadvantage is that their ionic conductivity at room temperature is pretty low, typically 1/100th to 1/10th of a millisiemens per centimeter, which is 1 to 2 orders of magnitude below what you'd want. They work much better when heated to around 60 or 70 degrees Celsius, because the polymer chains become more mobile and the ions can hop faster. And in fact, there's a company called Bolloré that actually deployed polymer solid-state batteries in a car-sharing program in Paris called Autolib, starting around 2011. Those batteries ran warm. They had heaters to keep the electrolyte at operating temperature. It worked, but the energy cost of keeping the battery warm and the limited power output at lower temperatures were real constraints. So each family of solid electrolytes has strengths and weaknesses, and a lot of the research right now is about hybrid approaches, combining a ceramic with a polymer, for instance, to get the high conductivity of the ceramic with the flexibility and good contact of the polymer, or coating sulfide electrolytes with thin oxide layers to improve their stability. The materials science is genuinely fascinating, and it's one of those problems where progress requires advances on multiple fronts simultaneously. But here's the thing that makes solid-state batteries so tantalizing, and why companies like Toyota, Samsung SDI, QuantumScape, and Solid Power have invested billions of dollars. It's the lithium metal anode. If you can make the solid electrolyte work, if you can get it thin enough, conductive enough, and mechanically robust enough, then you can pair it with a lithium metal anode and get a step change in energy density. We're talking potentially 400, maybe 500 watt-hours per kilogram at the cell level, compared to 250 or 270 for the best lithium-ion cells today. That's the kind of jump that could give an electric vehicle 600 or 700 miles of range, or let you build a much lighter battery pack for the same range, which saves cost and weight everywhere else in the vehicle. QuantumScape, a Silicon Valley startup that spun out of Stanford and went public in 2020, has been one of the most visible players. They're working with a ceramic separator. They haven't disclosed the exact composition publicly, but it's believed to be in the oxide family. And they've published data showing cells that can charge from 0 to 80% in 15 minutes, which is remarkably fast. Their approach is what's called anode-free. The cell is assembled with no lithium metal on the anode side at all. Instead, lithium plates out from the cathode onto a bare copper current collector during the first charge, forming the anode in situ. This simplifies manufacturing because you don't have to handle thin lithium metal foil, which is soft, sticky, and extremely reactive. But it means the solid electrolyte has to perfectly control where and how that lithium deposits every single cycle for thousands of cycles. If lithium starts growing unevenly, if a dendrite nucleates and pushes through the electrolyte, the cell shorts and it's over. Toyota has taken a different path, focusing on sulfide-based electrolytes, and they've been filing patents on solid-state battery technology for years. By some counts, more patents than any other company. They've announced plans to introduce solid-state batteries in vehicles by the mid to late 2020s, though timelines in this field have a habit of slipping. The manufacturing challenges are real. Making a thin, uniform, defect-free solid electrolyte layer at automotive scale, we're talking millions of cells, is a completely different problem than making a few cells in a lab. Every pinhole, every crack, every microscopic impurity is a potential failure point, and the cost has to come down dramatically from where it is today. Now, while solid-state batteries get a lot of the headlines, they're not the only beyond lithium-ion technology worth knowing about. Let's talk about a completely different approach to the battery problem, one that's less about maximum energy density and more about a different set of priorities: sodium-ion batteries. And the beauty of sodium-ion is that it's almost a mirror image of lithium-ion, built on the same intercalation principles, but using sodium instead of lithium. Why would you want to do that? Well, think about abundance. Lithium is not exactly rare, but it's not evenly distributed around the world. The largest reserves are concentrated in a handful of countries: Australia, Chile, Argentina, China. And as demand has surged with the electric vehicle boom, lithium prices have been volatile, spiking dramatically in 2022 before falling back. Sodium, on the other hand, is everywhere. It's in seawater, it's in rock salt, it's the sixth most abundant element in the Earth's crust. It's cheap, really cheap. And for applications where you don't need the absolute highest energy density, grid-scale storage, for instance, where the batteries just sit in a warehouse and don't have to be light, sodium-ion could be transformative. The chemistry works on the same basic principle. Sodium ions shuttle back and forth between two intercalation electrodes, just like lithium ions do. The cathodes can be layered oxides similar to the ones used in lithium-ion, or a class of materials called Prussian blue analogs, or even polyanionic compounds like sodium vanadium phosphate. On the anode side, there's a clever material called hard carbon, a disordered form of carbon that has voids and defects where sodium ions can tuck themselves in. You can't use graphite the way you do in lithium-ion because sodium ions are bigger than lithium ions, and they don't intercalate well into graphite's layered structure. But hard carbon works, and it can be made from biomass. Coconut, shells, wood, even sugar. There's something poetically satisfying about that. CATL, the Chinese battery giant that we mentioned earlier in the context of lithium iron phosphate, announced their first-generation sodium-ion cell in 2021 with an energy density of about 160 watt-hours per kilogram. That's lower than lithium-ion, definitely, but it's respectable. And CATL has said they're targeting integration into vehicles for shorter-range urban applications. A Swedish company called Northvolt and a British startup called Faradion, which was acquired by Reliance Industries in India, are also pushing sodium-ion toward commercialization. The cells can be manufactured on existing lithium-ion production lines with relatively minor modifications, which is a huge practical advantage. You don't have to build entirely new factories. And here's a detail that might surprise you. Sodium-ion cells can be discharged all the way to 0 volts for shipping and storage, which makes them safer to transport. Lithium-ion cells always have to maintain some charge, and transporting them involves hazardous materials regulations. Sodium-ion sidesteps some of that. But the story of alternative battery chemistries goes even further than sodium. There are people working on zinc-air batteries, aluminum-ion batteries, magnesium batteries, iron-air batteries. And that last one is particularly interesting. A company called Form Energy, based in Massachusetts, has been developing an iron-air battery designed specifically for long-duration grid storage. We're talking about storing energy for 100 hours, 4 days, at a cost they claim will be around 1/10 the cost of lithium-ion on a per kilowatt-hour basis. The chemistry is almost absurdly simple. Iron rusts during discharge, absorbing oxygen from the air, and then during charging, the rust is converted back to iron and the oxygen is released. Iron rusting and unrusting, over and over. The raw material is iron, one of the cheapest and most abundant metals on Earth. The cells are big and heavy, totally unsuitable for a car or a phone, but for a stationary installation sitting next to a solar farm in the desert, weight doesn't matter. What matters is cost per stored kilowatt-hour over thousands of cycles. And that's where iron-air starts to look really compelling. Think about it this way. If you're a utility company and you've built a massive solar farm in Arizona, you've got this wonderful problem where you're generating way more electricity than anyone needs in the middle of a sunny afternoon. You need to store that surplus so you can release it in the evening, overnight, through a cloudy day, maybe through several cloudy days in a row. Lithium-ion can handle the 4-hour window pretty well. Charge in the afternoon, discharge through the evening peak. But what about a week-long weather event? What about the dead of winter, when solar output drops and demand for heating spikes? That's where 100-hour storage changes the game entirely. And Form Energy's pitch is that their iron-air cells, despite being bulky, despite being heavy, despite having round-trip efficiency somewhere around 45 to 50%, which means you lose about half the energy in the charge-discharge cycle. Despite all of that, the sheer cheapness of iron makes the economics work for that use case. You're not paying for cobalt or nickel or even lithium. You're paying for iron pellets and some potassium hydroxide electrolyte. The company announced a deal in 2023 with Georgia Power to build a 15 megawatt, 1,500 megawatt-hour system. That's 100 hours of storage at rated power. They're building their first commercial factory in Weirton, West Virginia, in a former steel mill, which has a nice poetic symmetry to it. Iron being processed in a building that used to process iron for a completely different purpose. Now, that round-trip efficiency number deserves a moment because it illustrates a really important concept in energy storage. When we say a battery has 90% round-trip efficiency, like a good lithium-ion system, that means if you put in 100 kilowatt-hours of electricity, you get 90 back out. 10% is lost as heat during the chemical reactions, internal resistance, all the usual suspects. Iron air at 45 to 50% means you're losing roughly half the energy. That sounds terrible, right? And for a phone or a car, it would be terrible. You'd essentially need twice the solar panel to get the same usable energy. But here's the thing. If your goal is seasonal storage or multi-day storage, and the alternative is building natural gas peaker plants that burn fossil fuels, then losing half the energy from a solar farm that's already built and already generating surplus electricity you'd otherwise curtail, just throw away. Suddenly, 50% efficiency on nearly free surplus electricity. Looks pretty attractive compared to the alternative. The math changes when the input energy is essentially free. That's a principle worth sitting with for a moment, because it applies across a lot of energy storage thinking. The best battery isn't always the most efficient one. It's the one whose total cost of ownership, including the cost of the energy you feed it, makes the most economic sense for a particular job. And this brings us to something broader that's been reshaping the entire battery industry over the last decade or so, which is the idea that there probably isn't going to be one battery chemistry to rule them all. For most of the 20th century, you had a handful of dominant chemistries: lead acid for cars and backup power, alkaline for consumer disposables, nickel-cadmium for rechargeables. And each one had its lane. What's happening now is that we're entering a much more diverse ecosystem. Lithium-ion in its various cathode flavors, NMC, NCA, LFP, dominates portable electronics and electric vehicles and short-duration grid storage. Sodium-ion is carving out a niche for stationary storage and potentially low-cost urban EVs. Iron air and other long-duration technologies are targeting that 100-hour-plus window. Solid-state batteries, if they ever reach mass production, could push the energy density ceiling for premium EVs and aerospace. Each chemistry has its sweet spot, defined by the intersection of energy density, power density, cycle life, safety, cost, and material availability. And material availability, let's talk about that, because it's become one of the most consequential forces shaping battery development today. For years, the battery conversation was mostly technical. How do we get more energy into less space? How do we make it safer? How do we make it last longer? Those questions haven't gone away, but layered on top of them now is this enormous geopolitical and supply chain dimension that would have seemed almost irrelevant to the electrochemists of the 1970s. Here's the landscape. Lithium is found in significant quantities in Australia, Chile, Argentina, and China. Cobalt, which you need for NMC and NCA cathodes, comes predominantly from the Democratic Republic of Congo, where something like 70% of the world's supply is mined, often under conditions that raise serious human rights concerns, including artisanal mining operations that use child labor. Nickel comes largely from Indonesia, the Philippines, and Russia. Graphite for anodes is dominated by China, which also controls a huge share of the refining and processing for nearly all these materials, even when the raw ore is mined elsewhere. So you've got this situation where the push toward electrification, electric vehicles, grid storage, consumer electronics, is creating enormous demand for a set of materials whose supply chains are concentrated in a small number of countries, some of which are geopolitically complicated. This isn't just an abstract policy concern. It directly shapes which battery chemistries get investment and which get built. The rise of LFP, lithium iron phosphate, that we talked about earlier, part of its resurgence is absolutely about performance and safety, but a big part is also that it contains no cobalt and no nickel. You're removing two of the most supply chain vulnerable materials from the equation. Tesla's shift toward LFP for its standard range vehicles, BYD's heavy use of LFP in the Chinese market. These are partly engineering decisions and partly supply chain decisions. Similarly, one of the most attractive things about sodium-ion is that sodium is everywhere. You can get it from seawater. There's no concentration risk. No single country controls it. Iron Air takes this even further. Iron is literally one of the most common elements in Earth's crust. The United States Inflation Reduction Act, passed in 2022, put this supply chain logic directly into law. To qualify for the full EV tax credit, a vehicle's battery has to meet increasingly strict requirements about where the critical minerals were extracted and processed, and where the battery components were manufactured. The percentages ratchet up year by year. By 2027, 80% of the value of critical minerals has to come from the US or countries with free trade agreements, and no minerals at all can come from foreign entities of concern, which is a diplomatic way of saying China and Russia, primarily. This legislation is reshaping where battery factories get built, which chemistries automakers choose, and how mining companies plan their operations. It's industrial policy on a massive scale, driven by the recognition that batteries are becoming as strategically important as oil was in the 20th century. And it's not just the US. The European Union has its own battery regulation, passed in 2023, which includes requirements for recycled content. By 2031, new batteries sold in Europe must contain minimum percentages of recycled cobalt, lithium, nickel, and lead. That's pushing the development of battery recycling infrastructure, which is its own fascinating engineering challenge. When a lithium-ion battery reaches end of life, whether from a phone or an electric vehicle, the cells contain valuable materials, but they're intimately mixed together in a complex layered structure that wasn't designed with disassembly in mind. The two main approaches are pyrometallurgy, essentially smelting the cells at high temperature to recover metals, and hydrometallurgy, which uses chemical solutions to selectively dissolve and separate the materials. Hydrometallurgy generally recovers more materials at higher purity and with lower energy input, but it's more complex and generates chemical waste streams that need managing. Companies like Redwood Materials, founded by former Tesla CTO J.B. Straubel, and Li-Cycle in Canada, are building large-scale hydrometallurgical recycling plants. Redwood Materials, based in Nevada, has said their goal is to produce cathode and anode materials directly from recycled batteries, creating a closed loop where old batteries become the feedstock for new ones. There's something deeply satisfying about that idea, isn't there? The whole history we've been tracing, from Volta's pile of zinc and copper discs in 1800, through Plante's lead plates, through the lithium revolution, has been a story of finding the right materials and putting them in the right arrangement. And now, 2 centuries later, we're starting to think about those materials not as something you dig out of the ground once and eventually throw away, but as something you cycle and recycle, the same atoms of cobalt or lithium passing through battery after battery after battery. It mirrors the electrochemistry itself when you think about it. The whole principle of a rechargeable battery is that the chemical reaction is reversible. Ions shuttle back and forth, and the materials are reused with each cycle. Recycling just extends that same logic to the macro scale, to the life cycle of the battery as a product, rather than the life cycle of a single charge. But we're getting ahead of ourselves a little, because there's one more piece of the modern battery story that ties together almost everything we've talked about: the chemistry, the manufacturing, the supply chains, the policy. And that's the gigafactory. The term was coined by Tesla when they announced their partnership with Panasonic to build a massive battery cell production facility in the Nevada desert near Reno. Construction started around 2014, and the facility, known as Gigafactory 1, was designed to produce more lithium-ion battery cells annually than the entire world had produced in 2013. That's a staggering ambition. The logic was simple but powerful. Battery costs are driven heavily by manufacturing scale. The more cells you produce in a single optimized facility, the lower the cost per cell. Through economies of scale, process optimization, reduced logistics, and learning curve effects. The well-documented phenomenon where every doubling of cumulative production volume tends to reduce costs by a consistent percentage. For lithium-ion batteries, that learning rate has been remarkably steep. In 1991, when Sony launched the first commercial lithium-ion cell, the cost was somewhere around $12,000 per kilowatt-hour of storage capacity. By 2010, it had fallen to about $1,100. By 2023, the industry average was around $139 per kilowatt-hour, according to Bloomberg Neff's annual survey. That's roughly a 98% cost reduction in 3 decades. Almost nothing in industrial history has followed a cost curve that aggressive, except maybe solar photovoltaics, which have their own remarkable story. And Tesla's gigafactory concept catalyzed an arms race. Today, there are gigafactory-scale battery plants being built or planned on every inhabited continent. CATL, the Chinese company we mentioned, is the world's largest battery manufacturer and operates enormous facilities in Fujian province and is building plants in Germany and Hungary. LG Energy Solution and Samsung SDI in South Korea, SK Innovation, BYD in China, Northvolt in Sweden. The list keeps growing. The US alone has seen announcements for dozens of new battery plants since the Inflation Reduction Act passed, representing hundreds of billions of dollars in investment. Each of these factories is essentially a temple to electrochemistry at scale. Climate-controlled, clean rooms where electrode slurries are mixed, coated onto metal foils measured in microns, dried, calendared, cut, stacked or wound, filled with electrolyte, sealed, and then put through careful formation cycles where the cells are charged for the very first time and that critical SEI layer forms on the anode surface. The precision required is extraordinary. A single metallic particle, smaller than a grain of sand, contaminating an electrode during coating can create an internal short circuit that leads to a cell failure months or years later. Quality control at this scale is one of the hardest problems in modern manufacturing. Think about it. You're producing millions of cells per month, each one containing dozens of layers of electrode material thinner than a human hair. And every single cell needs to perform within a tight specification window for the next 10 or 15 years inside someone's car or someone's home energy system, a defect rate that sounds impressively low in any other industry, say 1 in 10,000, would be catastrophic here. 1 in 10,000 cells failing in a battery pack that contains several thousand cells means you'd expect a failure in nearly every pack you ship. So the target is more like 1 defective cell in every 10 million, maybe even better. That's Six Sigma territory and beyond, and achieving it requires an almost obsessive attention to the manufacturing environment. The air inside these coating rooms is filtered to remove particles down to a few microns. Humidity is controlled precisely because even a tiny amount of moisture reacting with the electrolyte can produce hydrofluoric acid, which corrodes the cell from the inside. Workers wear full clean room suits. The coating machines themselves are marvels. They spread electrode slurry onto copper or aluminum foil, moving at speeds of tens of meters per minute. And the wet coating thickness has to be uniform to within a few microns across the entire width of the foil. If it's too thick on one side, that part of the electrode will age differently, and the cell's capacity will degrade unevenly. If it's too thin, you lose energy density. Cameras and sensors monitor the coating in real time, measuring thickness, detecting pinholes, flagging any anomaly. And then, the coated foil goes through enormous drying ovens, sometimes 50 or 60 meters long, where the solvent evaporates in a carefully controlled temperature profile. Too fast, and the binder that holds the active material particles together migrates to the surface, and you get poor adhesion. Too slow, and your throughput drops and costs go up. After drying comes calendaring. The coated electrode passes through heavy rollers that compress it to a precise density. This step matters more than you might think. The porosity of the electrode, how much empty space is left between the particles, determines how easily lithium ions can flow through it during charging and discharging. Too dense, and the ions struggle to penetrate, which hurts power capability. Too porous, and you're wasting volume, which hurts energy density. There's a sweet spot, and hitting it consistently across kilometers of electrode material is genuinely difficult. And here's the thing. All of these steps happen before you even assemble a cell. Once the electrodes are cut and stacked or wound with the separator between them, they go into a casing, get filled with electrolyte in a vacuum to make sure the liquid wets every pore of the electrode, and then sealed. The formation process that follows, where the cell is charged for the very first time, is where that SEI layer we talked about earlier grows on the anode surface. The conditions during formation, temperature, current profile, duration, directly influence the quality and stability of that SEI, which in turn affects how the cell will age over its entire lifetime. Some manufacturers spend days on formation and initial testing. It's expensive, tying up cells and equipment for that long, but it's how you catch early defects and ensure consistency. Now, all of this precision costs money, obviously. But here's what's remarkable about the gigafactory model. By doing it at enormous scale, With high automation and continuous process improvement, the cost per cell keeps dropping. And that cost reduction is what's making the energy transition possible. Because batteries aren't just a nice technology, they're increasingly the linchpin of the entire shift away from fossil fuels. Let's step back and think about why that is. You've got two massive sectors of the global economy that are responsible for the bulk of carbon emissions: electricity generation and transportation. For electricity, the cheapest new sources of generation in most of the world are now solar and wind. That's not aspirational, it's just economics. But solar and wind are intermittent. The sun sets, the wind dies down. And electricity demand doesn't follow the weather. So you need storage. You need a way to capture energy when it's abundant and release it when it's needed. And that's batteries. Not exclusively. Pumped hydro, compressed air, hydrogen, thermal storage all have roles to play. But batteries are the most flexible, the most scalable, the fastest to deploy, and increasingly the cheapest for durations up to several hours. And with technologies like Form Energy's iron-air system targeting 100-hour storage at very low cost, batteries might eventually cover multi-day storage too. For transportation, the story is simpler in some ways. An electric motor is fundamentally more efficient than an internal combustion engine. Something like 85 to 90% of the electrical energy reaching the motor gets converted to motion at the wheels, compared to maybe 20 to 35% for a gasoline engine. The rest becomes waste heat. So the question was never whether electric drive was better. It was whether you could store enough energy on board, affordably, in a package that wasn't too heavy or too large. And lithium-ion batteries crossed that threshold. A modern electric vehicle with a battery pack costing maybe $8,000 or $9,000 at the cell level can travel 300 miles on a charge. That was unthinkable in 2010, when the same range would have required a battery costing $40,000 or $50,000. And the cost curve hasn't flattened yet. Bloomberg Neff and others project that lithium-ion pack prices could fall below $100 per kilowatt hour within the next few years, which is widely considered the point at which electric vehicles reach upfront purchase price parity with comparable gasoline cars without any subsidies. Some analysts think we'll get there by 2026 or 2027. When that happens, the economic argument for buying a gasoline car essentially disappears for most use cases because EVs are already cheaper to fuel and maintain. The battery, which was the bottleneck for over a century. Remember those early electric cars in the 1890s that lost out to gasoline precisely because of energy density and cost, is finally catching up. But I want to be honest about the challenges that remain, because this story isn't one of uninterrupted triumph. Mining lithium, cobalt, nickel, and the other materials that go into batteries has real environmental and social costs. Lithium extraction from brine deposits in South America's lithium triangle, Chile, Argentina, Bolivia, uses enormous quantities of water in some of the driest places on Earth. Hard rock lithium mining in Australia generates waste rock and requires significant energy. Cobalt mining in the Democratic Republic of Congo, as we discussed, involves serious human rights concerns alongside the industrial operations. Nickel mining and refining, particularly in Indonesia, which has become the world's dominant nickel producer, involves deforestation and, in some cases, the discharge of mine tailings into the sea. These aren't problems to wave away. They're real, and they require real solutions. Better mining practices, stricter environmental regulations, supply chain transparency, and yes, recycling, which we touched on earlier. The European Union's battery regulation, which started taking effect in stages from 2023, is the most ambitious attempt yet to mandate recycled content in new batteries. By 2031, new batteries sold in the EU will need to contain minimum percentages of recycled cobalt, lithium, nickel, and lead. That creates a guaranteed market for recycled materials, which in turn justifies investment in recycling infrastructure. Companies like Redwood Materials in Nevada and Li-Cycle in various locations are scaling up to meet that coming demand. And the push toward chemistries that use more abundant, less problematic materials, lithium iron phosphate instead of nickel and cobalt cathodes, sodium-ion batteries that eliminate lithium entirely, is partly driven by these supply chain concerns. It's a kind of elegant feedback loop. The problems created by scaling one chemistry drive innovation toward alternatives, and the whole ecosystem of battery technology gets richer and more resilient as a result. So where does all of this leave us? Let me try to paint a picture of the battery landscape as it exists right now, in the mid-2020s, because it's genuinely one of the most dynamic areas of technology and industry on the planet. Lithium-ion, in its various flavors, NMC, NCA, LFP, dominates. It powers your phone, your laptop, your electric car if you have one, and increasingly, the grid-scale storage systems that utilities are installing at a furious pace. LFP is surging, especially for applications where energy density matters less than cost, safety, and longevity. Stationary storage, standard range vehicles, commercial vehicles. NMC and NCA still lead for premium EVs, where you want maximum range in minimum weight. Sodium-ion is entering commercial production, targeting the cost-sensitive applications where lithium-ion's performance advantages aren't necessary. It won't replace lithium-ion for your smartphone or your Tesla, but for grid storage and low-cost urban vehicles, especially in markets like China and India, it could be transformative. Solid-state batteries remain the tantalizing next frontier. Toyota has said it aims to introduce solid-state batteries in vehicles by the late 2020s. QuantumScape, Samsung SDI, and others are in various stages of development and pilot production. If someone cracks the manufacturing challenges, making solid electrolytes cheaply, maintaining good contact between solid layers as they expand and contract, achieving the cycle life that lithium-ion already delivers, the jump in energy density and safety could be dramatic. But the key word is if. The battery industry has seen many promising lab results that stumbled on the path to mass production. Iron air and other long-duration technologies are just beginning their journey from demonstration to deployment. Form Energy's factory in West Virginia is under construction. If it works as promised, 100-hour storage at a fraction of lithium-ion's cost could fundamentally change how we think about grid reliability and the role of natural gas peaker plants. And behind all of these specific technologies, there's a deeper truth that I find genuinely beautiful, and it's worth sitting with for a moment. Every single one of these batteries, from Volta's simple pile of zinc and silver discs in 1800 to the lithium-ion cell in your pocket, to the solid-state prototypes in labs right now, works on the same basic principle. You have two materials that want to react with each other. You separate them, so the reaction can only happen by sending electrons through an external circuit, which gives you useful electrical current, while ions shuttle through an internal electrolyte to complete the circuit. That's it. That's the whole idea. 225 years of battery development is really the story of finding better and better pairs of materials, better electrolytes, better structures, better ways to make the reaction reversible, better ways to keep everything stable over thousands of cycles. It's the story of understanding matter at finer and finer scales, from Volta's intuition about contact between different metals, to Faraday's laws of electrolysis, to the quantum mechanical understanding of how lithium ions nestle between layers of graphite or cobalt oxide just a few angstroms apart. Each generation of scientists and engineers inherited the puzzle from the last and pushed it a little further. Good enough didn't come from nowhere. He built on Whittingham's work, who built on the understanding of intercalation chemistry, which depended on crystallography, which depended on X-ray diffraction, which depended on the discovery of X-rays themselves. The chain of knowledge stretches back and back, each link depending on the ones before it. And the people in this story, they're worth remembering. Volta, stubborn and proud, insisting that electricity came from the metals themselves. Faraday, the bookbinder's apprentice who became, arguably, the greatest experimental scientist who ever lived. Planté, patiently rolling his lead sheets. Goodenough, still publishing papers in his 90s, driven by an almost spiritual conviction that a better battery could help the world. Yoshino, quietly perfecting his carbon anode in a corporate lab in Osaka. The thousands of unnamed engineers in gigafactories right now, monitoring coating lines and tweaking formation protocols, doing the unglamorous daily work that turns laboratory breakthroughs into the products that change how civilization works. You carry the result of all their efforts in your pocket. You might charge it tonight before you fall asleep, not thinking much about it. And that's fine. That's actually the highest compliment you can pay to a technology, when it works so well that you forget it's there. But now, maybe, when you plug in that cable and hear the little chime that says, "Charging has started," you'll think for a moment about the lithium ions leaving the cobalt oxide cathode, drifting through the electrolyte, slipping between the graphene layers of the anode. Billions of ions, each one carrying a single positive charge, making that journey in both directions every day of the battery's life. A tiny, silent, reversible electrochemical dance that took 2 centuries of human ingenuity to choreograph. And the dance isn't over. Tomorrow, someone in a lab somewhere will try a new electrolyte formulation, or a new cathode structure, or a new manufacturing technique, and they'll get a result that's a little bit better than yesterday's. The cost curve will tick down another fraction of a percent. A battery will last a few more cycles. A car will go a few more miles. A grid will store a few more hours of sunshine. It's incremental, mostly. Quiet work. But it adds up. It always adds up. So, let that thought settle. Let the chemistry do its quiet work in whatever device is playing this for you right now. The electrons are flowing. The ions are shuttling. And everything is exactly as Volta would have hoped even if he couldn't have imagined it. Rest easy with that. The batteries will keep going while you sleep.